I will start discussion on a new topic which is stresses in the soil mass due to external loadings. Until now we have discussed about the internal stresses in the soil mass, and these internal stresses are, let us say, pore water pressures or because of the self weight. Now what we are going to do is we are going to talk about the situation where I would like to know how the soil is going to respond when external loading is applied to it. Now in engineering applications this concept has a lot of significance, and most of the problems which are being tackled by the consulting geotechnical engineers would require these type of concepts to be practiced. So let me first bring to your attention the types of situations where the stresses in the soil mass due to external loadings become very important. The first situation could be or we may say this is the real life. Say I have the ground surface and somewhere here there is a footing which is being placed. So this is the column and this is the foundation, and this happens to be the soil mass. It is understood that this column is going to take load P, and hence the footing is going to transmit a pressure Q on the soil mass. I would like to understand what is the state of stress at this point P, and this point P can be defined in such a manner that I can say that this is the radial distance R and the depth of this point is Z. So basically it has the coordinates R Z. I can include theta also here, it could be R Z and theta. So this is situation number 1. When you construct foundations, I would be eager to know what is the state of stress in the soil mass. There could be another situation like suppose if I have a multi-story building, so this is a multi-story building, and situation like let us say Cuff Parade and most of the populated cities in the world where the cost of land is extremely high. So you can't afford higher spacings between the buildings. So suppose if I ask you a question, what should be the safe distance at which I should be designing or I should be constructing another building? Remember, space is extremely important, very expensive, alright. So this is the building which is sitting on the foundation system. Now because of construction of building B, if the building A was already existing, what has happened? The state of stress at a given point P, which I have taken over there, has changed. So PA has changed to PB, alright, and I would like to understand whether this system soil is capable of taking this type of loads or not. Alright. So, this is again the soil mass. There could be a situation number 3 where I am sure when you travel all along the highways or the railways, what you observe is they are the pipelines which are carrying water. So, suppose this is the embankment of the railways. So, this is the, let us say, embankment on which the train is moving. It is an embankment. Made up of soil, and this is the railway track. It could be an airstrip also, or this could be a highway, a pavement. Alright. And somewhere you must have noticed what we do is we carry, let us say, some utilities. So, this is the utility pipeline, and I want to see whether do not go by the elevation. This could be x, this could be y. Most of the time x is going to be less than y, and hence I will try to understand, because of the movement of the traffic, what I have done is I have simulated 3 type of traffics. One is the railways, another one is the aircraft, the third one is roadways. So, I would like to understand whether this pipeline is safe or not. That means, because of the movement of the vehicles here, what is going to happen to the pipelines. Alright, this could be buried pipelines also. So, I would like to find out what is the state of stress somewhere here. Again, the point P shifts. Now, point P could be in anywhere in the domain, and I would like to do the analysis. There could be a third situation. We have been talking about fourth situation. This is the ground surface, and as we discussed in the last lecture, the application of sheet piles. I would like to create a bulkhead over here. So, this becomes a bulkhead. This is the soil mass or water, this could be storage, and I would like to know what is the state of stress at a point, let us say somewhere here, somewhere here, somewhere here. Now, suppose if I remove the piles, this is a sheet pile, and if I say that in a simple situation where I have the ground surface and I would like to retain an embankment, the same embankment which we have created over here. So, this is the embankment, and this embankment can be utilized for creating, let us say, oil foundation, tank foundations, storage, whatever. So, suppose if I want to find out the moment I have created this embankment, what is the state of stress at different points in the soil mass. So, P might be varying here, P, P1, P2, P3 and so on. What has changed over here is that the type of loading which we have has become a triangular loading. At this point the loading intensity is 0. As you go this side, the loading increases to Q max and then it remains constant. So, this becomes a typical loading condition which we are imposing on the soil mass. There could be another situation where we might be doing excavations. So, this is let us say the loading of the soil mass, and this could be let us say excavation. I would like to excavate the soil and I would like to create a facility like this. So, this is the initial ground surface and this becomes the final ground surface. If I remove this much of the material, this much material has been removed, and I want to find out after removal of this material what is the state of stress at this point, because ultimately this system has to stay stable, is unsupported. Here this is supported with the help of a sheet pile, alright. So, these are different examples of the situations which we might come across in today's civilization. What I want to know is what is the state of stress at point P. Define the state of stress at point P. And why we want to do this? Because if I know the state of stress at point P, I can link it with the yield strength of the soil. You may think of any other situation which you think is practical. I may create a situation like this also. Suppose if I do a let us say detonation of an explosive, alright. So, what I will do is I will bury the charge over here and I can charge it. So, what is going to happen? This is going to create shear waves, compression waves, and because of this the state of stress is going to change at point P. So, these are very critical situations which you may come across, alright. So, what we will do is the general principle remains same except for this situation where I have talked about the blast loading which is a different scenario altogether. Rest 1 to 6 we can easily solve by considering the concepts which I am going to discuss in the class today, alright. And as an undergraduate student, as a beginner in the subject, you should be aware of situations 1 to 6, how to analyze them, fine. The best way to define the state of stress in the soil mass because of the external loading is by considering the Bosonisk equation or Bosonisk philosophy. So, as I said, we are talking about the stresses in the soil mass due to external loadings. This is where the Bosonisk theory is used. In 1858, this was proposed by Bosonisk. What this theory states is that for homogeneous soil mass which is isotropic in nature, which follows the constitutive relationship that means elastic modulus is defined Poisson's ratio is defined, and hence we are assuming the soil to be linearly elastic material. Okay. One interesting thing is that this soil mass has been assumed to be weightless. Did you notice this? That the soil mass has been assumed to be weightless. Why? We are making the soil mass devoid of its weight, because weight causes the internal stresses in the forms of either sulfates or the pore pressures. So, it has been assumed that as if we are computing the state of stress in ether. Sometimes these type of soils are also known as ponderable soils. Check it on net, what is the meaning of word ponderable. These soils are talking to themselves, they are pondering, they do not know the way they have been modeled. Their properties are different, but somebody is modeling them in a different manner. So, if these relationships are valid, homogeneous, isotropic, constitutive relationship is valid, weightless material, and the point load, the external load which is acting on the soil mass is a point load. Where do you come across point loads? As I said, foundations of columns. So, the moment I say raft, this is not a point load. So, foundations of the columns are point loads, alright. If I convert it into a raft, this becomes a uniformly distributed load area wise. So, as per this, if you have the soil mass which is exposed to an external loading of Q, and if I want to find out what is the state of stress at a point P in the soil mass, the radial distance is R, this distance is capital R, and another assumption here is that the soil mass happens to be semi infinite soil mass. That means the extent of the soil mass is semi infinite. We call it as a semi infinite soil mass, alright. Soil mass happens to be semi infinite. Semi infinite means if this is the direction of Z, this is the direction of X, and if this is the direction Y, we are considering the domain. So, soil mass is nothing but the domain in which we are doing the stress analysis. This happens to be alright semi infinite. So, Z is tending to infinity, X is tending to infinity, Y is tending to infinity. So, this is the domain in which we are doing the stress analysis. What is the state of stress at point P? The state of stress in point P would be normally, let me change the nomenclature, we take this as Z and this as Y, this is as Z. So, basically this is sigma Z, the normal stress which is acting at point P, sigma R. I am sure you are doing a course in RCC also this semester. So, suppose if I give you a ring of finite thickness, alright, and suppose this is a pipe which is carrying some fluid and if I ask you to show the annular stresses, we call them as hoop stresses. So, hoop stresses will be acting in the periphery, circumference, alright. So, these are the hoop stresses. So, we have sigma z, we have sigma r. There could be a stress in the direction also, but because I have assumed this to be isotropic in situation, and hence sigma z is equal to sigma y, clear. If you draw the state of stress at this point, you have done engineering mechanics and you have done mechanics of solids. This is sigma z, sigma r, we will be having the shear forces tau z r, okay. And if I want to come out of this coordinate system, I can always use the Cartesian coordinate system. If I define this theta and if I say that this is r and theta, is this okay? So, this I am assuming as z, this distance, and if you look in the 3 dimensional at point P, there is a component of r which is a function of x and y. Is this okay? If you look in the 3 dimension, this state of stress has been defined as, this will be x and y, correct. So, this will be in xy plane because that we have already taken, alright. So, r will be under root x square plus y square. So, this is the plane in which this point is sitting. So, as per the bosonics, the equation is for the point load, sigma z equal to 3q upon 2 pi into z is cube upon r square plus z square to the power 5 by 2. This can be simplified to 3q upon 2 pi z square, and this becomes 1 upon 1 plus r by z square to the power 5 by 2. I think this one is easy to remember, alright. Q is the load, z square is a sort of a area. So, this becomes a pressure term, 3 upon 2 pi is the solution. Normally what we do is, we replace this term as IB, and this is what is defined as the influence factor, alright, influence factor IB. I am sure you must be realizing that state of stress in the soil mass is totally devoid of its properties. What are the properties? Normally we define the properties of the soils or the soil mass as density, void ratio, porosity, saturation, unit weight, pore water pressure, okay. What else? Poisson's ratio, engineering properties. These are the fundamental properties, bulk properties. Engineering properties are elastic modulus and Poisson's ratio. So, these are the soil properties, none of them appear in this expression, because the way the Bosonics theory has been derived, this is for weightless material, alright. Now, sigma r is q upon 2 pi, this is 3 r square into z upon, but yes, if you can remember, that is okay. One minus 2 mu upon r square plus z square plus z r square plus z square to the power alright. Sigma theta is defined as q upon 2 pi 1 minus 2 nu negative sign z upon r square plus z square to the power 5 by 2 minus 1 divided by this term. If I use this term as, let us say, capital X, so this becomes capital X. Now, there is an interesting thing. If Poisson's ratio is equal to 0.5, which is for saturated soils, saturated clays particularly, sigma theta becomes 0. The fourth stress which we have not still considered is tau ZR, the shear stress. The shear stress would be 3q upon 2 pi rz square over r square plus z square to the power 5 by 2. If you solve this equation, the Bosni's equation which has been used, you will get this sigma theta as the negative term. State of compression, and you must be realizing that all these stresses are compressive. So, if you are let us say if you take a plate and then compress it from both the sides, there could be a bulging. So, the bulging indicates the negative pressure. So, sigma theta is going to be tensile in nature. Now, what we can do is, so you can replace all these coefficients with influence factor, alright, IB. Hence, I can write sigma z equal to 3q upon 2 pi into IB, and z square also 2 upon 3 upon 2 pi also I can take into IB, and I can say that this is a function of q upon z square. Now, do you find any abnormality in this expression? See, we started with the point load because the Bosni's equation is for the point loads. Now, suppose if I say that z tends to 0, or for that matter, if let us say I said r tends to 0 and z tends to infinity, where this point would be? R tends to 0 means on the z axis and z tends to infinity. This is one of the situations in which I will be interested. The second equation would be, the second thing in which I will be interested is z tending to 0, r tending to 0. So, z tending to 0, r tending to 0 is this point, clear. So, what is the stress at this point? Sigma z tends to infinity, clear. So, this is the issue, because what you are doing is, when r and z tend to 0, this becomes a point load, the stress at this point is going to be infinity, one of the abnormalities of the solutions. Anyway, no problem. We as an engineer, we will still go ahead with these solutions and we will try to see how these things can be sorted out. So, If you look at this influence chart, if I substitute the values of R and B and R and Z, and if I get the values of IB in that expression, for R by Z equal to 0, the IB is 0.4775. You can compute this for different values up to 6.15, and this will be tending to 0.001. So, for all practical purposes, I can write that at R equal to 0, now this is a very interesting solution which we have obtained. There are two possibilities of getting this, either Z tends to infinity, then only we can get R by Z equal to 0, or a better possibility will be R equal to 0 itself. So, this is a solution when R equal to 0, we say that sigma Z equal to 0.4775 Q upon Z square. Now, the point is, this is the solution which normally is used to obtain the sigma Z. Now, what I want to do is, I want to use the Bosni's theorem or Bosni's relationship for developing three things. The first thing which I want to develop is the isobars for the point load. We call it as a isobar diagram. The second thing is, we want to do the pressure distribution. So, when I say pressure distribution, this is your sigma Z, sigma R, sigma theta, tau R Z. This is the state of stress acting at a point P because of the external loading Q. So, pressure distribution on a horizontal plane and the third thing would be to get the pressure distribution on a vertical plane. Fine. So, these three things I want to do. Now, let me introduce the concept of the isobars. Isobars are the contours of equal vertical stresses. That means, if sigma Z remains constant and if I plot the pressure lines or the pressure contours, they become isobars. So, these are the contours of equal sigma Z vertical pressure. How would you plot them? Now, I am sure you can realize from here, if what is the form of this equation? Between sigma Z and Z, Q is a constant, is it not? So, what is the form of this equation? If I write like this, Z square into sigma Z is constant. Suppose this is y square into x equal to constant. What is this graph? Hyperbola. Clear? So, that means all the contours of the stresses are going to be hyperbolic functions. That means, if I take, let us say, Q, and this is the point and this is my Z direction. If I plot, let us say, 10% of Q as sigma z, oh not sorry 10%, 90% let us say, where this would be sitting? It would be sitting like this. Please mind the discontinuity at this point which we discussed just now. So, at this point the function is discontinuous, it would look like this. It is not a circle, it is a hyperbolic function. So, this is corresponding to 1. As the intensity of the pressure decreases, what will happen? Somewhere here you will have, this would be let us say sigma z equal to some 50% of Q, and this will go up to certain value where I may say that sigma z has become let us say 5 or 10% of the Q value, because this influence factor is doing all the tricks. You are right, but see if you look at this point, again this is nothing but the point P1, P2, P3 and so on. So, R is changing, Z is changing, which is getting absorbed in this term. IB is a constant term which represents R by Z. So, that means a better way of writing this would be, I can say IB into Q upon Z square, the stress term. So, this I can write as stress term sigma. So, IB is a function of RZ. So, basically the contours of these pressure bulbs, we call them sometimes, we call them as isobars, are inclusive of R and Z, and they depict the state of stress, alright. Now, this is one thing which we wanted to do. The second thing which we want to do is, we want to do the pressure distribution. So, if this point is Q, and if I ask you to draw the vertical pressure distribution and the horizontal distribution of the pressures, this is the ground surface at a depth of Z. If I create a plane, this is the plane at which I want to see the variation of sigma Z, as if you are cutting all these pressure bulbs along this axis. So, if there is a plane which is passing through this is the same plane as what I am showing over here. So, the pressure distribution would be like why the rutting takes place of the pavements. This is the answer. So, excessive loading, the tire pressure from the vehicles creates the maximum intensity of the pressure at a certain distance Z, just below the point of application, and beyond which what happens? It fades out. So, the moment R tends to infinity, what happens to your sigma Z value? This tends to some constant value at this plane, otherwise this is going to be the maximum value. So, this is the pressure distribution in the horizontal plane. As a transportation engineer, particularly if I am working on the materials, I will be very much eager to know, if I am designing a runway, let us say, I always give this example when I travel particularly with pilots. I do not know whether you are aware or not, but most of the runways are designed based on the layered theory, multiple layers of the material sitting over each other. This is layer number 1, layer number 2, layer number 3, layer number 4. We play with the stiffness of the material. So, stiffness of the material is defined as epsilon and Poisson's ratio and elastic modulus, and the thickness. Okay. So, if I want to minimize the influence of the sigma Z on a horizontal plane, what I should be doing is, I should be playing with this cross section so that I can nullify the effect of sigma z, and I can make it a point that at this point sigma z p is going to be much less than sigma yield. This is what you will be studying in your transportation engineering course. This is how the pavements are designed. Fine. Now, another interesting thing which I would like to do is, I would like to plot the variation of stresses on the vertical plane. So, as if I am cutting this whole thing across a vertical plane. So, this is, let us say, AA, this was BB. So, this is BB and the AA would be, if this is Q, these are the contours of, this is what I have written there, these are the pressure bulbs, contours of equal sigma z's known as isobars. So, this whole yellow color bulb is going to be representing sigma z equal to 90-95% of the stresses which are getting transmitted to the soil mass. Not the inside part, these are the contours of the points, he was discussing each and every point on this surface is going to be of 90% Q value. So, that is why we call them as contours of equal sigma z's, fine. So, as you come deeper, the pressure intensity is decreasing, this becomes only 5 to 10% of the Q value, and you can use this expression which I had written over here to compute what is the state of stress, and you can plot it over here. So, this would be a function like this, it cannot increase. So, I have to curtail it somewhere here, okay. So, starting from a very high stress value, the sigma z is decreasing as z increases. So, this becomes the variation on a horizontal plane, this is the variation on a vertical plane. Now, depends upon what type of problem you are dealing with. Suppose I am designing a pipeline, buried pipeline, there could be a situation that this is my buried pipeline. This project I did recently for Santa Cruz airport. I hope you were aware that the airport used to be shut down for several hours during March and February. So, it is an active runway, runway cannot be stopped permanently, but I am sure next time when you are traveling, you should see there have been 2 pipelines which of the oil which have been taken across the active runway. That means the landing and taking off operations are occurring, and you would like to take out some utility across the runway. Simple analysis like this can help you. I can define what is the zone of influence of the pressures, and I can negotiate by locating the pipelines there. Every time I cannot be so lucky, so then you have to do engineering based on the material properties and whatever. Anyway, so giving you an example, suppose this is how the load comes, alright, and I want to see whether this pipeline is going to get influenced because of the external loading or not. If I know the value of Q, I can find out what is the state of stress at the crown of the pipe. Pipe is made up of some element, either structural element would be steel or mild steel or concrete or whatever, and then I can compute what is the yield strength of the pipe, and then we can design it accordingly. Fine. This is another good example of where the application of these type of computations would be in real life. So, it is always the vertical stresses which are going to be much more detrimental as compared to in plane or perpendicular to the plane stresses. But suppose if I am designing a tank foundation, which you must be seeing big tank forms, in your structure. So, this becomes a ring foundation. Normally the oil tanks are seated on the ring foundation. I need not to spend so much money because rafts are going to be expensive. What I will do is I will cut them into ring. Is this okay? So, as if a ring is bearing the entire load of the tank. In this case, your sigma theta is going to be very important, r theta, because this is going to be the hoop stress here. So, this design will be based on sigma r theta. However, coming back to your question, why we are only interested in sigma z, because sigma z happens to be the most critical stress which is going to govern the stability of the structure as well as the soil mass. In case yield occurs at any of these points, your structure cannot remain stable. We will discuss these things in the second course, fine. Now, let us discuss the concept of superimposition of the loadings. How many types of superimposition principles you have studied until now? So, there you superimpose, is it not? Suppose there is a cantilever and I can superimpose the load in such a manner to get a certain value of the deflection. What is the name of this method? Structural analysis. Suppose I started with the first situation, there is Q1 acting here and there is Q2 acting here, and find out what is the state of stress at any point, let us say somewhere here. So, the best way of doing this would be you assume them independently, find out the state of stress corresponding to Q1 first at this point, Q2 at this point, and sum them up. So, sigma z will be equal to summation of, if I have series of loads over here, this will become sigma z at point P because of Q1. So, this becomes I equal to 1 to n. Have you understood this? So, what I have done, a point load has got converted into a line load. Practically there is no difference between the situation, where several Qs are acting all along the line. Okay. It could be UDL also. Why not? Suppose if you take a plane on which there are several Qs are acting, several Qs. Now, if I integrate on the surface, this is the integration over the line. Now, if I integrate over the surface, this is going to give me the net effect of a loaded area of certain area of cross section. So, very simply I have converted the context of the situation. From point load, where we were defining the stresses at r equal to 0, z equal to 0, I have created a uniformly distributed load in the form of the line load and uniformly distributed load on the area. It's okay. The rest is all integration. Is this okay? So, if I integrate over these things, I will get the same effect. In other words, as long as the situation is very simple, I can keep on clubbing for Q1, Q2, Q3, Q4, Q5, Q6, and I will say that this is the total sigma z acting at this point. So, suppose if I ask you to find out the second situation, from point load we will move on to the uniformly distributed circular area. Until now we have talked about a foundation system, where this is the column. So, this is the point load. the best possible approximation would be that the Q is acting at a given point, though the foundation also is of finite size, but this is approximation as compared to the domain of semi infinite soil mass. Clear? Now, when I come to circular area, circular footings, is a good example. I might be having a situation like this. This is the area which is carrying a uniformly distributed load of Q, where Q is equal to capital Q upon area of cross section. And suppose if I ask you to find out what is the state of stress at a given point P. So, this whole thing is resting on the ground, and because of this you want to find out what is the state of stress at point P. You have done a lot of integration in your 10 plus 2 or whatever rather than 10 plus 2. So, suppose if I consider an element at a depth as a radial distance of r, small r, this is the radius of r, the entire area, and if I consider a small element over here as dr, okay, r into dr, clear? Area of cross section of this can be known, that will be 2 pi r into dr, and if I know the loading intensity Q, it gets multiplied by small q, this is the load, nothing so great. What I have done is the entire circular area which is uniformly distributed loading, I have converted again it to a point load, and I am assuming here that the circular loading is also an assembly of several point loads acting on the soil mass. Fine, is this okay? So, your function sigma z equal to 3q upon 2 pi z square IB can still be used. I will replace this by del of sigma z, and now IB is the tricky term. So, this is a function of r by b, r by z, clear? So, this q is equal to this one. So, I can substitute this value over here and I can integrate. So, I can get the expressions for the sigma z due to the circular loading. Is this part clear? Fortunately, I hope you will realize the way we assumed IB over here in case of point loading. If you remember what we did, we simply said sigma z equal to q upon z square into IB. Okay. So, this term you can form a table, and that table you can always refer to for different r by z, and you get the values of sigma z. The same thing you can do over here also. Conceptually things are same. Fine. Another interesting thing, sometimes what we do is rather than having a circular footings, we might be having, let us say, strip footings. Whenever you see your fencings in the hostel or in the buildings, you know, fencings or maybe compound boundary walls or compound walls, they are all sitting on a foundation which goes in the one dimension. Why? This is the foundation part which will be extending up to infinity. When we say infinity, when the width of the foundation B and thickness of the foundation is much smaller than the length of the foundation. Clear? This becomes a strip footing, one dimensional footings, because their width and thicknesses are very small as compared to the length. Yes, you need not to worry. Now this again has become a line load situation, clear. So you can integrate over all intermediate Q values and you can find out the stresses acting at a point. What is going to change is, I hope you will realize that this dr term which is going to come over here, when you integrate it, this is going to be dr. So here r has to be from 0 to r, clear. And what about this z term? This will be from the given point to the point where you are interested in finding out the pressure. So that means 0 to z. Same thing you can do over here. So this becomes a case of strict footings, circular footings. Now whenever you make embankments, as far as the foundation part is concerned, this is nothing but the strip foundations, embankments. Embankments are nothing but the dams which we were discussing in the previous lecture as far as the seepage analysis was concerned. So you have certain specific width at the base, slopes 1:n, 1:m, if you remember. We have to define the height, we have to define the top width of the embankment, and this embankment also tends into infinite length, railway embankment. So railways are passing through kilometers of lengths of these type of embankments, agreed? So suppose if I ask you to find out what is the state of stress at the bottom point, no problem, you can still model it. The entire loading can be, now there is a trick. The load is going to act over here, the railways are going to run over here, the roadways are here, okay, aircraft loading is here. We have to delegate this stress at the base of the embankment, clear? I use the word delegation. So for a better word for this is dispersion of the loading. So suppose there is a Q load which is acting, and I want to find out what is the state of stress in the gross terms as a designer at a depth of, let us say, z, and I do not have time to do this analysis. I mean, I am just doing first DPR to tell you what is the cost of the project. So I do not want to go into the intricacies, I do not know how much time is going to take me to analyze all these things. What I can do simply is there are 2-3 ways of dispersion of the loads. The first one is we normally use the concept of 45-degree dispersion angle. That means if this is the Q, I will disperse it on this plane at 45 degree. These are thumb rules. So I am sure you can realize now, if this is Z 45 degree, this is also going to be Z, clear, and this is also going to be Z. So basically Q has been delegated to 2Z, and then the third dimension is perpendicular to the board. So this becomes your loaded area. What I have done is I have delegated the stresses from this point to this point. So when you design foundations, normally we give a foundation pad. So what this is going to do, I get 2-3 advantages. I have created a pad for the foundation system and I have reduced the stresses. This is engineering. Another method of dispersion would be, sometimes they have a tendency to disperse it at 30-degree angle. I mean, don't ask me from where it has come. This is just based on people's whims and fancies. So this 45 degree becomes a 30-degree angle, alright. This is also valid for, let us say, there is a finite foundation of width B, thickness, and if I want to disperse this load on this plane which is at a depth of Z. So, if I use this angle of dispersion as alpha, this is going to be what, Z tan alpha, and this is also Z tan alpha plus B. So, this basically this whole stress is getting transmitted now on a plane which is of area of cross section 2 times Z tan alpha. You must be wondering how these constructions are done on the marshy lands. This is a trick. Hope you are getting the point, mechanistic point. Is this clear? If I expose the marshy lands to direct loading, nothing can be done. You can't even stand there. But if I create a good foundation pad, I can disperse the load. Depending upon the Z, this area is going to be extremely higher, and hence the bearing can be obtained. Now, something of interest would be uniformly loaded rectangular areas. To make our life easy, there was a person known as Fadam. This person has already given charts. So, we call them as Fadam's chart. The beauty of these charts is, if you have a uniformly loaded area which is rectangle of length L, width B, and please understand that these methods have limitations, or they are particular methods. So, you can find out the state of stress only at the edges at a depth of Z, point P, alright. Now, let me first interpret this graph. It is a very longish expression. The influence factor would be 1 upon 4 pi 2 mn m square plus n square plus 1 upon m square plus n square plus m square n square plus 1 multiplied by m square plus n square plus 2 over m square plus n square plus 1 plus tan inverse 2 mn m square plus n square plus 1 to the power half upon m square plus n square minus m square n square plus 1. Fine. So, please do not remember ever, where m is equal to b by z and n is equal to l by z. It does not matter if you interchange b or l. So, it does not matter whether m or n get replaced or interchanged. Conceptually, these are nothing but the graphs which look like this, the Fadam's chart. This is the influence factor IB, this is m, and then this is how the n varies. Alright. This is a peculiar solution, one of the solutions I would say. If you have a uniformly loaded area of B and L, and if you have to find out the state of stress exactly at the edge or the corner point of the loaded area, alright. Manipulations can be done in several ways. I hope you will realize and you may enjoy that if I have a uniformly loaded plate, let me not segmentize it first. Suppose this is the plate or this is an area where Q is known. So, I hope you remember that sigma z will be equal to IB into Q by Z square, clear. So, the moment you get IB from this charts or this equation, just substitute over here, you get the value of sigma z. Now, suppose if I ask you to find out what is the state of stress just beneath the CG of this loaded area at a depth of, let us say 10 meters. Can you use Fedham's chart? No is also correct, because look at this situation. So, it has to be at the just beneath the corner, okay. So, what I can do is I can discretize this whole thing in such a manner that I will create 4 units out of it, clear. Now, I think you can understand, I can apply this concept, fine. Is this clear? So, 1 unit at the edge, no issues, I can find it out. Another unit at the edge, I can find out. Another unit at the edge, I can find out. 4th, and I will superimpose all of them as if there were 4 sectors Q1, Q2, Q3, Q4, done. No issues, very good. Suppose if I say find out this is the loaded area, let us say foundation, and I want you to find out the state of at this point. Please remember, when I say state of the stress point, this point means in the z direction at a certain depth, clear. How will you use this concept now? Do a bit of geometry. Is this okay? So, I can do like this. I have made this section as a subset of a bigger square, and I can solve it. Apply your mind a bit and try to understand in what way the context of the application of Fedham's chart has changed. The loaded area is only this much, agreed? So, if I use method of superimposition, what I will have to do? If this is A, B, C, D, and what I have done is I have projected it on a bigger scale, A prime, B prime, A double prime, A triple prime and D prime, clear. So, if I have to find out the state of stress at this point using these charts at depth z, I will find out with the whole thing as the rectangle. So, A double prime, A prime, B prime, B, C, D, D prime, A triple prime, A double prime, clear. So, this becomes my rectangle. First compute the state of stress through this. This place area does not exist, clear. Now, how would you use the superimposition principle? You will have to subtract the effect of stress which is coming because of extended portions, that is it. So, method of superimposition can be done in 2 ways. Either you club the stresses, make them summed up, or you can use them as a subtraction also. So, this portion is not contributing, and hence I can subtract the stresses which are going to come because of this strip, and in the process what has happened, this strip has come 2 times. So, add once, clear, and then you have the bigger one, apply the correction. You remember what we did, this was the loaded area and you were trying to find out what is the state of stress over here. So, this is just a way to apply Fadden's charts for computing the state of stress. It is very simple as far as the mechanics is concerned, but the application part is going to be very interesting. So, when you enter into the field where you are a consultant and when you are applying these concepts, how do you apply these concepts? Very interesting situations. Look at the modern day failures. I do not know how many of you are watching the YouTubes where the major failures are occurring in the eastern part of the country or the dams. Are you aware of this? What this system is going to do over here? Suppose, see where the litigation comes in the picture. You are getting this point where you will earn money. I do not know whether you have ever realized this or not. This is your house, you are living comfortably over here, and then one day one builder comes and starts constructing something over here. Now, what is going to happen? Is this situation not similar to the one which we have analyzed just now? You are living over here and then some activity is going to happen over here. So, this Q has become Q plus delta Q, and because of this Q plus delta Q, at this point the state of stress is changing, and we have done a lot of analysis. You know, we have computed sigma total, we have computed sigma prime, we have computed pore pressures. So, that means all this is going to create a detrimental effect. Okay, so this is one example problem. Second example problem, I might be having my house here and tomorrow railways decides to take a railway track close to my home. Are you going to allow? And do these computations in a clandestine manner and do not disclose that your house is going to be safe. So, I can find out because of this extra loading what is going to happen at this place, vibrations in another issue. As far as the loading is concerned, I can find out how the state of stress is going to change and whether this is going to be acceptable to me or not. Fine, because from next lecture onwards we are going to talk about the application of all these concepts in the form of consolidation. So, if I am constructing something over here and if this system gets distressed, and God forbid if this happens to be a heritage building, but then somebody has to safeguard that let this operation go on and we take guarantee that nothing is going to happen to the heritage building. So, you cannot just say like this. What you will be doing? You will be doing simple stress analysis and show, here we are talking about loading. Now, look at another situation. Your house is here and I am doing excavation inside. So, I have created three situations. Now, a person like me cannot sleep over here because I am an expert in my subject. Things which appear to be very simple on the blackboard and the paper, when they get delegated into the real life, is the practice of the subject, which is very, very interesting.